Okay, this is our next lecture on linear programming with Maple. And the idea is to introduce one more Maple command or set of commands that can be very useful for us. So we're going to start with problem 3.2-4. This is at least a problem in the 11th edition. And clear everything from the computer. So I'm going to solve this problem in two ways. One is the way we did previously, and the other is with the new Maple command. So the first thing I do is open plots, because there are two plots that I'm going to use a lot here. One is unequal, that's graphing inequalities, and the other is contour plot. So in this problem, there's an objective function. It's z, and z of x1, x2 is a function of two variables. It's 500x1 plus 300x2. So this in Maple is the syntax for defining a function of two variables. There are three constraints, and I'm going to list them this way in square brackets. So in square brackets, in each constraint separated by a colon, by a comma. So 15x1 plus 5x2 at most 300, 10x1 plus 6x2 at most 240, 8x1 plus 12x2 at most 450. And again, you'll notice I always put in the time sign, the multiplication symbol. It's not always necessary. Sometimes it is. It's never wrong. So I just always put it in. So this is my objective function. These are the constraints. And I can use the unequal plot command to graph the feasible region. So it's all the region, it's the region in the XY plane and x1 and x2, x1, x2 plane. The variables are non-negative. I'm just making that clear by letting x1 start at 0 and x2 start at 0. And if you graph the feasible region, that's what it looks like. Now, the graphical method for solving a linear programming problem is to find where, if you're trying to maximize the objective function, you want to find the point in the feasible region where the objective function z is as large as possible. Now, for any constant value of z, this is going to be a line. And for different values of z, you have a family of parallel lines. These are the contours. And here I'm giving the command to contour plot my function z of x1, x2, x1 going from 0 to 60 and x2 from 0 to 60, and coloring the lines red so they'll stand out versus the blue. And I'm going to call this objective for objective function. And for a given value of z, if you look at the objective function, 500x1 plus 300x2, if you solve this for x2, if you put this equation in slope-intercept form, the larger the value of z, the higher the x2 intercept. So you want to find the line parallel to these red lines, which hits the x2 axis, the vertical axis, as high up as possible and intersects the blue. And just to get some idea of what's happening, we superimpose the contour lines on the graph of the feasible region, and you get this picture. I'm using the display command. Actually, if you look at this, it looks like, you can never be sure, but it looks like the red contour lines are actually parallel to this line of the feasible region, this boundary line. But we'll prove, this is the simplex method, that the maximum value or the minimum value of the objective function always occurs at one of the corner points of the feasible region. And this feasible region has 5 corners. 1, 2, 3, 4, 5. And we want to see where you have the maximum value. It looks like it'll be at this point or this point. So we can solve, so this corner point is the intersection of this line and this line. And this corner point is the intersection of this line and this line. So this corner point you get by solving the 2 equations, because these 2 lines, one is 10x1 plus 6x2 equal 240. Sorry, 15x1 plus 5x2 equal 300. And this is the other. And when you solve those lines, you get this point of intersection is 15, 15. And when you evaluate the objective function at that point, you get 12,000. If you solve the 2 linear equations and 2 unknowns to find this point of intersection, this corner point, you get 5 halves and 215 over 6. And when you evaluate the objective function there, you also get 12,000, which says that these 2 points are maximum values of the objective function. And in fact, any point on the line between them, this whole boundary line in the feasible region, every one of those points maximizes the objective function. So the general theory will say that the maximum value occurs at a corner point, but you can also have the maximum value occurring at other points. But you always do get the maximum value just by looking at the corner points. There might be more points, but no point will exceed that, and other points might be equal to it. Okay, so now this is the new command for today. There's a package of commands in Maple called optimization. You open the package with the with command, so with optimization, and you get 1, 2, 3, 4, 5, 6, 7, 8. You get 8 new commands that we can use. And the one we're interested in is LP solve. Now you can always go to help. There's help, Maple help. Search for LP solve. And you get a lot of information about how to use this command. Let me just show you how it works in practice. So I'm going to use the LP solve command. And I have to tell it different things. First, what is the function I want to, what is my objective function? It's z of x1, x2. What are my constraints? Here I created this set of constraints. It's these 3 inequalities in the square brackets. Do I want to minimize or maximize the objective function relative to the constraints? I want to maximize it. And assume equals non-negative means I'm only going to look for non-negative values. So when I hit enter, I get 12,000 as the maximum value, and one point at which it occurs is 15, 15. So this is really all we needed to solve the problem. Just I needed to have defined the objective function. I needed to have put down the constraints, maximize or minimize, and that's it. So that really is a little valuable piece of information. Okay, I'm going to stop at this point. And tomorrow I will work out a couple of other problems and post on the video with this.